for the indexing session later this afternoon. It'll probably be done in interpretive dance. I don't think I'm going to have any voice left by the end of today. Anyone coming to SQL Saturday Iceland on Saturday? No, okay. Good, so you don't get to hear the 8-hour pre-con that I'm going to have to do on Thursday somehow. Anyway, so this is a session on weight stats. I'm going to look at SQL's execution model. I'm going to look at some of the common weight types and talk about what they are, what they aren't, mostly about what they aren't, and why so much information you find online is completely and totally false. Before we get started though, some admin. Neil wants you to know what's happening for the rest of the day. So this session finishes at 2:30. Another session, 2 more sessions. There is a raffle draw at 6:15. If you want to win something, you do have to be here. If they call your name and you're not here, they simply throw it away and give it to someone else. So I do recommend you stay here for that. There looks like some quite nice prizes outside. I don't know what Neil's got planned for the evening session. I'm sure he has something quite pleasant planned. The sponsors, I've said thank you to all of them. Right, and the interesting things. Sorry if there's any sponsors in the room. I'm not slighting. I won't get into this. So this is what we're going to cover this afternoon. Why weight stats are interesting in the first place. We've heard a lot about them. Why we care, why we're interested, why we're even spending time looking at this. I'm going to spend some time on SQL's execution model so you can see why such things as weights occur and how you should interpret them. And briefly look into monitoring weights, not in too much detail because there's a million blog posts on the subject. And the majority of the time I want to spend on interpreting some of the weight types and why not you should and shouldn't be concerned about them if you have them. And please, if you've got questions, shout. This is a small enough room. Can take questions. I don't mind spending longer on one thing if anyone's interested. So, why are we interested? If we go back roughly 10 years, more than 10 years, then we were at a very primitive era in SQL performance tuning. If you walked up to a server in those days and someone said this is badly performing, typically there was no good place to start. There was no accepted methodology, there was no accepted method of figuring out what is wrong with the server if it's a server you've never seen before and all you know is it's not working well. In the 2005 timeframe, a couple of very bright guys wrote a document that's still available on the Microsoft website called the Weights and Queues Methodology for SQL Performance Tuning. If I recall, one of them was from SQL Cat and one of them was from PSS. I could be mistaken, but they were both working at Microsoft, both heavily involved in SQL performance tuning. And what the Weights and Queues methodology lets you do is take a server that you've never seen before, and by looking at the weight statistics, what the various processes within the server are waiting for, and the queues, which is the list of things that are waiting. So what are we waiting for and how many things are waiting for it? Just by looking at that, we've got somewhere to start with looking at the server's performance. It lets you very quickly identify what the problematic areas were on the server. So you could walk up to a server and say, hang on. Within 5 minutes, you can say, hang on, this thing is bottlenecked on CPU, and you don't spend time digging into why the disk latency is high. It's not the relevant problem. That is the link for the article. It is still available. I will caution you, however, it's aged very, very badly. The methodology is still as valid as it was in 2005, but the rest of the article is unfortunately quite wrong these days. So if you're going to go and read it, I'd say go and read the introduction and the first page or two and then forget the rest. The general methodology is great, but the advice on what to do is no longer valid in most cases. It's worth reading. if you keep in mind that this was written for the era of 2 processors with maybe 2 cores each and 16 gigs of memory with a large server. Who's got 16 gigs of memory on their laptop these days? Yeah, absolutely. Anyone with more than 16 gigs on their laptop? Yeah. Okay, who's got the biggest server in the room? Most memory? Anybody? Terabyte of memory. Anyone want to beat that? 2 terabytes of memory. Can we keep going? Okay. 2 terabytes of memory. Back when SQL Server was 2005, came out, and this article was written, 2 terabytes was a large number for disk space. 2 terabytes of memory was unheard of. And bear in mind, this was written at the beginning of the 64-bit era for SQL Server as well. So the methodology is great. The rest of the article, the what to do for these weight stats, not so much. So that's some cautions on that. Everyone happy with this so far? Before I go on too much further, who is a DBA in this room? I assume most of you. Okay, and the rest of the people? Developers? Okay. Anybody actually in the consulting business where you end up seeing a lot of strange servers on a regular basis? Okay. I am. I very seldom work on the same server 2 weeks in a row. So this is pretty much how I start doing analysis for servers, a modified version of this. If you're working with your own servers, the methods are going to change slightly because you no longer need to identify the problematic area. You're more looking for what has changed since yesterday, last week, last month. What's going to give me an indication that things are going wrong. It's a slight difference. Most of the same theories does apply though. Okay, so the SQL execution model. This is important if we're going to understand why weights and queues are interesting. So when you submit a query to SQL Server, you've got a session to SQL Server, the query starts running. SQL will allocate 1 or more threads to that query. If your query is running serially, 1 core, you'll get 1 thread. If it's running in parallel, you'll get more, potentially a lot more. And by the way, the number of threads is not related directly to the max degree of parallelism. You can end up with a huge number of threads for a single query. As an example, if I've got a single query on a server with a max stop of 4, and I've got 3 distinct parallel sections to my query, I can end up with 15 or more threads. They won't all be running, but I can have that many threads. So your executing request has got 1 or more threads associated with it. Each thread is bound to a scheduler. And threads are bound to schedulers. They cannot move between them. Once a thread is on a scheduler, that's where it stays. Each processor core that is visible to SQL Server has a scheduler for it. So let's say you've got 2 quad-core processors with hyperthreading. That's 8 virtual cores. SQL will spin up 8 schedulers, plus about 3 more hidden schedulers. And it uses those schedulers to actually run the query. The schedulers are not bound to the CPUs unless you are using CPU affinity. If you're defining the processor affinity, then you're also binding the schedulers to their processors. It's a side effect. It's not quite an unpleasant one, to be honest. If you're not using processor affinity, then each scheduler is free to be moved from one to a processor. So if one processor is idle, the SQL operating system can take a scheduler that's got a lot of work on it and put it onto an idle processor. As soon as you start playing with processor affinity, though, that's gone. All right, so this is roughly what a scheduler looks like, hypothetically, of course. So this is the actual executing. No, it's a process. Whatever's on here is actually executing. You can have 1 thread and only 1 thread on a processor at a time. We may have 16 cores in a server, but this is a single core. We have wait a list. This is the list of threads which are waiting for a resource. You can have a lot of threads in here. This is an unordered list. Then you have the runnable queue, which is the list of threads that are waiting to get back on the processor. So let's take an example. We've got a query that's running, and it started executing. The query would like to read a row from a page. The query processor looks for that page in memory. The query processor asks the access methods to fetch a row off that page. That page is not in memory. That page has got to be fetched from disk. That thread then gets a wait assigned to it. It has to go and wait until that page has been read in from disk. That thread gets put onto the waiter list, and it will wait there until that page has arrived from disk into memory. That thread does not execute again until something tells it that the I/O has finished. I'll get to what does that in a second. So let's say that thread sits in the waiter list for 10 milliseconds, and it's waiting for a page from disk. That's a page I/O latch wait. That thread has then incurred 10 milliseconds of page I/O latch waits. That thread then gets signaled to say, your page has arrived, it is now in memory. It doesn't go back onto the processor, it goes into the runnable queue. This is not ordered, this is ordered, so our thread goes to the bottom of the runnable queue. Now the only thing it's waiting for is spot here. If there's nothing ahead of it, it goes straight onto the processor. If there is, it'll wait for these guys to get their turns. Once it gets to the top, it gets put back on the processor so that it can run. The time in here is known as signal time. It is the time since the thread was signaled that its resource has arrived until it gets back on the processor. Does that make sense? Any questions on this? This is kind of important. I think that's about... Okay, so what does the signaling? An executing thread will also, as well as doing its own query work, also process I/O interrupts. In other words, the executing thread will also handle the, oh, that page has arrived, that page has arrived, that page has arrived, and do the signaling. So whatever's sitting on here does not execute at all, only executes when it gets back on there. So this thread that's sitting here is not waking up every now and again going, is my page here, is my page here? It's not. Completely gone to sleep, absolutely not going to execute until something calls it and says, hey, your stuff's here. If you're looking at the DMVs, wait time is the cumulative time here, and signal time is the amount of time here. It's just the way the DMVs are put together. Right. Everyone happy with that? All right, so monitoring waits. By the way, if you guys don't ask questions, we're probably going to finish way early. So, you have a question, yes?
When it falls on the processor, can it get kicked off for other reasons other than wait for time?
Can a thread that's on the processor get kicked off for other reasons other than waits? Technically, no, because SQL is not a preemptive operating system. So the SQL so take a few steps back. There are two methods of multitasking operating systems, two styles of multitasking operating systems. Windows is what we call a preemptive multitasking OS. The Windows kernel says, you are done on the processor, you go on. Because Windows cannot assume that everyone's going to be well behaved. Considering half the software we see these days, that would be a really bad assumption. So Windows assumes that things are not going to voluntarily yield the CPU, so it throws them off. SQL is a cooperative scheduling OS. It assumes that threads are going to voluntarily yield the CPU once they're done. They can be done because they're finished. They can be done because they need a resource. They can be done for another reason, which I'll get to when we get to that wait type, particular wait type. But a thread will always voluntarily yield the processor. Now, it does get amusing when you've got SQL and Windows getting together, because Windows is still a preemptive OS. SQL assumes that the threads are going to voluntarily yield. That doesn't stop Windows from taking this entire thing and saying, you off. But that's not a yield. That's not a wait. That's the thread is still sitting executing. It's just been shoved off the processor by Windows while something else runs. Yes?
And if you write an infinite loop, just like a while loop, it counts to...
And if you write an infinite loop, you're writing T-SQL, it's interpreted. The actual execution engine still knows what it's doing, and it will still voluntarily yield the CPU. It doesn't have a wait, we'll get to that. That's called a scheduler yield. When we get to that wait type, that's the other type. It's not a wait, but the SQL OS, the query processor, the loop may be infinite, but the query processor will still say, hang on, this is done long enough, I will yield the processor. Anyone remember extended stored procedures written in C++? Yeah, they could not. They could choose not to. Because they were written in C++, they were outside of the SQL, well, 2000 didn't really have the SQL OS, but the extended stored procedures, which is a really bad idea, by the way, written in C++, were outside of the SQL OS's control, SQL processor's control. They could essentially just sit on the CPU forever and not do a damn thing. This, by the way, is called a non-yielding scheduler. Anyone seen a non-yielding scheduler stacked up before? Yeah. That's a bug. It's a bug. That's why they stack dump and die. You're supposed to call PSS with those. That means that a session has not yielded when it should have. And SQL OS has got no way of regaining control because it cannot preempt, because that's not how it's built. It's got to wait for whatever the hell that was to voluntarily yield, and if it can't, you end up with problems. I've actually seen a server crash because every single scheduler was non-yielding. That was SQL 2000 on an Itanium. It was a really bad idea. But yes, we had 12 schedulers, all non-yielding. SQL just crashed, basically. Not pretty. Oh, CLR, by the way, is still under control of the SQL OS. If you write an infinite loop in CLR, it will still voluntarily yield. You can't write low-level code low-level enough to defeat the query processor any longer, unless you want to write extended stored procedures again. Answer your question? Answer your question. Okay. All right, so how we monitor these things. As I said, I'm not going to spend a lot of time on these because every blog post under the sun talking about weights talks about these three. So, DMOS wait stats. This is cumulative since SQL Server started or somebody last cleared this DMV. The two columns you're most likely to be interested in this are wait time and signal wait time. Wait time is the combination of the time spent in these two. Signal wait time is the time spent here. So if you want to know how much time was spent as a resource wait, you subtract the two. Keep in mind that when you're looking at very low durations, there's measurement inaccuracies there. Where SQL still uses the low precision timers, so you've got a 3-4 millisecond inaccuracy. It's not usually a concern. SysDM OS waiting tasks. That is a list of sessions, or sorry, threads, which are sitting here. Doesn't count things in the runnable queue, it's just things that are sitting waiting for a resource. And then if you want to know the runnable queues, you can get the count of them, only the count of them, from OS schedulers. This is boring. I said everything under the sun does it. A few points. Cumulative since SQL Server started. I see a lot of forum posts that go and get the top 10 wait types out of this ordered by Max, ordered by their wait time, and say, what's wrong with my server? Dude, I've got no bloody clue. Because you've just shown me a number and given me no context. Okay, the wait time on this wait was 17,462,756. And how long has that server been up? If it's been up longer than 12 hours, that number's probably quite useless. Because some of these wait types will show up high in normal operation. For example, if you're running backups, there's about 5 of them that go through the roof. This is not unusual, it's expected behavior. So if you are looking at a server for what the hell is wrong with the server, or what the hell is wrong with my server, what you want to do with this is take snapshots of the thing at intervals. 10 minutes, 15 minutes, half an hour, I'd say no more than an hour, because you start losing the granularity. Take snapshots and take the difference between now and previous, and that gives you a sensible idea of, okay, I have this wait type really high between 11 and 11:30 in the morning. What happens between 11 and 11:30 in the morning? It also lets you see, hang on, these wait types are really high between 8 and 10. Oh wait, I do backups between 8 and 10 p.m. So what? Why are my I.O. waits through the roof between 2 and 3 in the morning? Oh, because we're running CheckDB. Yeah. So there's certain things which are expected to shove the weights really, really high. If you're just looking at a number, not useful. That's about all with that. Oh yes, there's a lot of blog posts which talk about percentages of the total weights. They will show you that such and such weight was 62% of the total weights. Be very careful of those, because unless you're looking at the whole number, the percentages are fairly useless by themselves. I've got a screenshot I don't have it with me unfortunately, that showed that I think it was I.O. completion was 97% of the overall weights. I showed this to some people and said, what's wrong with the server? And they said, the I.O. subsystem is horribly slow. That's my laptop, by the way. And that's since I booted it 10 minutes ago, and it's been idle ever since, all the time. Whoops. So if you're going to take those queries and use the percentage of total weights, make sure you're also looking at how many weights there were, and you know over what time interval that was taken. One piece of information is fairly useless. For example, there, if I see that I've got, say, page I/O latch weights, those are weights for pages to be read from disk. If I see that those are taking up 95% of my total weights, I might be concerned. If I then see that my server's been up for 2 hours and my total wait time was 20 milliseconds, I don't care. So do be careful. This isn't something you want to take one number and look at. You want to have a look in context, the whole server, total durations, uptime, all that kind of thing. And that's why I say take that in intervals so that you know this is half an hour between this time and this time. You know what the server's like in that time. You can actually interpret the weights sensibly. This is transient, so as threads go in and out of the wait state, they will appear and disappear in that. So this isn't something that has cumulative values in it. If something is sitting in here and saying 20 milliseconds, it's been waiting for that thing for 20 milliseconds. If it gets that page, it'll go out. And bear in mind, that won't show for an entire query. Let's say we've got a query that's reading a 100 million row table that's not in memory. That thread is going to be in and out of this DMV, probably with page I/O latch weights for different pages. Want this page, want this page, want this page, want this page. So this is great for what's currently waiting, but you need the context of what the hell's that query actually doing as well. So tie this with exec requests, exec sessions, that kind of thing, because it does not give you the whole picture by itself. And then OS schedulers, yeah, it's just a count. Might be useful if you think you've got unbalanced CPUs, lots of threads on one scheduler, not on the other. Other than that, as I said, it's going to tell you how many things are waiting. Like waiting for the processor, runnable queue. That's about all that's going to tell you. Happiness? Yes.
So does that tell you if you have not enough CPU?
Does that tell you if you have not enough CPUs? Maybe. But you've got to keep in mind how long are things in that runnable queue. If I've got 6 things in my runnable queue and they're there for less than a millisecond in total, I might be fine. They're there for a longer time, I might start worrying. There's very few DMVs which give you the whole picture, so take it in context with everything else. If you consistently see this high and you see a lot of signal wait time, then you might start thinking, I have CPU. But by that point, you're also going to see your CPU sitting 80, 90%, probably flat. All right. Yes. Is that? I say you can clear DM OS wait stats, and that's a DBCC statement. I recommend you don't. Partially because it loses history. Partially because there's a lot of third-party monitoring tools that will go for a complete and total loop if you do that. They'll start recording negative wait times, which is really funny. Rather, take a snapshot of it, wait some time, take another snapshot of it, and have a look at the difference. It's far safer than actually clearing it. Because you go and clear it, and then you go and say, hang on, but I actually want to know how much I had. Oh, it's cleared. I can't do a thing. Anyone using Azure here? Azure SQL DB, not Azure VMs. Okay, it's sysdm DB wait stats for Azure per database wait stats. I don't think those have come down into SQL Server, the earthed version of it yet. I think we're still looking at only OS wait stats in the earthed version of SQL Server. But for Azure, you've got the per database wait stats. Okay, extended events. Now these get fun. This one's, I think, from 2014 onwards. It's a fairly new one. Before I talk too much about wait stats, who's still stuck with 2008 R2 or before? My condolences, guys. You do know it's out of support.
And we're upgrading to R2 as well.
You're upgrading to...
For one of the largest retailers in the UK, and I won't mention them.
I can guess. It's one of two. And knowing the IT, I can probably guess. Don't worry, I've got a large insurance company back home that is upgrading to 2008 R2, and they're very happy to do so. So, guys...
We're not happy to do so.
Well, no, the IT team's not happy to do so. The insurance company's very happy about how progressive they are. So, guys, you do know that thing's 8 years old. Well, 6 years old. Close enough. Okay, if you're on 2008 R2 or before, I'm sorry. Because these things, unless you want to get very friendly with XML and very, very friendly with some very unpleasant code, they do exist, but they're not very nice to use. Anyone on 2005? You're upgrading, so...
Just a few instances for upgrade.
Would you like a large hammer? I did a few times. Once it stops working, you can justify upgrading it. Yes, if you're on anything before 2012, sorry, most of this stuff doesn't work for you. This one, I think, is 2014. These are older. These go older, as in they were there in 2012, and I think in even 2008. All right, so wait info fires when a wait starts and when a wait ends. Suffice it to say, that's a very, very frequent event. Please be careful about actually putting an extended event session on it. Definitely be careful about putting a large payload on it. Extended events are a lot lighter weight than SQL Trace was. That doesn't mean they're free. It's entirely possible to crash a server using extended events if you try hard enough. I'll show you how to try hard enough. This is the kind of thing you do with either an aggressive filter in place or on a dev server, preferably both. So wait info... Sorry. Wait info, it's the column called opcode, which tells you whether it's the start or the end of the event. Wait info external is fired for the preemptive waits. That's waits that go outside of SQL Server. We'll talk more about preemptive waits in a few minutes. And wait completed obviously only fires when the wait completes. Now, if you want to find out exactly what caused the wait, there's a fun little trick on 2000 might only be 2012. But we'll see. All right, so our nice friendly extended event sessions. I've just taken the wait completed event. Now, I should mention this does require some setup, and I haven't done that setup on here, so I'm going to show you how this works, but I'm not actually going to show you the results of it. What this requires that you've done beforehand is gone and got the symbols, the public symbols for the version of SQL Server that you're working on. If you're not sure how to do that, Paul Randall's got a nice blog post. You can go read that. It is in the reference section. Well, one of Paul's blog posts that links to this is in the resources section. So you go and get the public symbols for SQL Server. Once you've done that, go and log the wait completed or the wait info events. Put aggressive filters in place, please. In this case, I'm filtering for latch X over 10 milliseconds. These are typically in microseconds, the durations in extended events. For actions, let's take those two out. Add the call stack. That's the Windows call stack. That's the actual internal offsets and procedure names that are getting called in SQL Server as this runs. You won't get too much, it's only 5 or 6 lines, but what that will give you is an idea, if you can read the stuff, of what led up to this wait being fired. If that's not enough fun, you can create a stack dump. Yeah, you can actually have SQL stack dump every single time it encounters that wait. Please don't do that on a production server. And if you're really the person who wants to see how things work, attach a debugger to SQL Server and select that one. SQL hits the wait, the executable breaks in the debugger. As in, you actually have the debugger with the position. Quite fun if you want to go playing around in the internals and guts of SQL Server. You need the public symbols to do any of those, otherwise you're just going to get a lot of memory addresses. Without the symbols, all you'll see is stuff like that, which is not very useful. With the symbols, you'll see stuff like this. It's obviously not very particularly easy, but and there's reasons you might want these call stacks, and I'll show you Paul's wait stats library later on, and you can see another reason you might want these. So that's a good example of how to kill a production server with extended events. Oh, and if you really want to kill the production server, that one's almost guaranteed to do the job. Yeah, that dumps every single thread out. Might I suggest you cover your tracks carefully before doing that? No, seriously, it's great to play around. That kind of thing definitely doesn't belong on a production server, though. So that's our extended events and our DMVs. Any questions at this point? Everyone's sleeping after lunch. All right, so quick show of hands. What do you think? Well, what do you think is the most misunderstood wait in SQL Server? CX packet. Anybody want to disagree with that? Okay. So I'm going to look at a bunch of waits where the frequently given advice online is somewhere between useless and stupid. Some of it is really, really bad. Yeah, CX packet only came in number 4. It's generally, the device is often bad. It's not generally that misunderstood. I see people screaming about these also as well. If there's any on here that I'm not mentioning, so if there's any that I'm not mentioning that you're curious about, feel free to ask. I can probably talk about most of the common ones anyway. There's over 200 weight types in SQL Server these days. They're getting very, very numerous. I can certainly talk about the more common ones if you want. So let's get into these. The background weights. There's a reason why most of the scripts you'll find for weights have a massive long list of where weight type not in, because there's a whole bunch of weight types which are completely normal, completely expected, and completely benign. Almost all of the background processes are in a weight type by default. Let's take, for example, the lazy writer. The lazy writer's job is to write dirty data pages from memory back to disk when there's memory pressure. There's a bunch of other things as well. The lazy writer spends most of its time doing nothing. And while it's doing nothing, it's posting lazy writer sleep as a weight type, because it has to. Because SQL Server's execution model requires that if it's not on the processor, which it's not, and it's not in the runnable queue, which it's not because it doesn't want to run, it has to be on the waiter list. And if it's on the waiter list, it has to declare a weight type. So it does. It declares a weight type of lazy writer sleep. Essentially, the lazy writer, I'm asleep. Wake me when something interesting happens. And that's exactly what SQL will do. When it's time for the lazy writer to do something, it gets signaled that it's no longer asleep. Hop into the runnable queue, onto the processor. So the lazy writer accrues lazy writer sleep at a rate of approximately 1 millisecond of wait every 1 millisecond of real time. More if you've got multiple NUMA nodes, because there's multiple lazy writers, one on each NUMA node. So if your server has been up for 3 days and you have 4 NUMA nodes on your server, you will be seeing roughly approximately 12 days of lazy writer sleep, which will put it at one of the top weights on the system. This is not a concern. In fact, if it wasn't up that high, I would be rather worried. The lazy writer should be lazy. If it should be asleep most of the time. If it's not, that's when something's seriously wrong. So when you're doing any form of weight analysis, make sure you've got that list of to be ignored weights. And by the way, it changes for every version of SQL Server because they keep adding more. And you filter all the benign and sensible ones out. So it's quite amusing. On the forum, someone posts I'm seeing these as my top 10 weights. What should I do? Nothing, 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 and nothing. Why don't you give me something to work with? Because all of the weights they posted were background tasks. And they will be, because those will be sitting almost at the top on most servers. You can also exclude most of the backup-related weights, unless you're trying to debug a problem with your backups. If you're not, then exclude them. They're probably not that interesting. They're not interesting for general performance tuning. So, I'm not going to bother listing them. Glenn keeps a diagnostic script very up to date. He's very punctual about this. Every new version of SQL Server comes out, he updates his diagnostic scripts. Go get his latest diagnostic script. Take his list of weight types to be ignored and use that. And yes, Glenn Berry diagnostic scripts on Google will find his stuff very quickly. I can't remember. His blog should be SQL Skills blogs, Glenn. Happiness? Shouldn't be all that difficult, I hope. And yeah, by the way, sleep, there's also the sleep weight type. Yeah, it's just a session that's asleep. It's not anything important. One thing I am not mentioning here, however, is the sleep task weight type, because it's actually not a background task. It's not a background process. It's usually benign, except when it isn't. So, we'll talk about that one separately. Sleep task, it's one of those catch-all weights. If a thread needs to get off the CPU, because it's waiting for something and it doesn't have a more sensible wait to use, it uses sleep task. This can come up when there's some parallel related things. It can come up when there's some spills to disk. It can come up in a bunch of other situations. It's one of those, I don't know what, I feel like getting off the CPU, I'm going to post a sleep task. Ignore it most of the time because it's usually completely benign. The only time I will say you want to pay attention to this thing is if you keep seeing it in DMOS waiting tasks with fairly long wait times. So if you're looking at what is currently waiting on the system, you keep seeing this pitch up, you keep seeing it pitch up with non-trivial wait times, then you probably need to do something about it because that's probably hash spills gone bad. Hash spills, when a hash table spills to tempdb. It posts a sleep task wait type. Don't know why. We complain to the OS, to the dev team, but it posts a fairly nonsensical wait type when it's writing hash tables and only hash tables into tempdb. So if you do see this thing keep popping up in OS waiting tasks, it's probably that you've got hash tables spilling to tempdb because the memory grants were inadequate, possibly because the row estimations were inadequate, could be your statistics are out of date, could be a bunch of other things. But it's probably going to be related to hash spills. Happiness? Yeah, it's a very esoteric one. As I said, most people just ignore this and it's usually safe to ignore. A question or just thinking? Okay, that's sleep task. A strange one. The preemptive waits. Okay, so we talked earlier about preemptive and cooperative multitasking. Windows is preemptive, SQL is cooperative. So when SQL needs to call out to Windows to get something done, like zero me out a file for me, get me some authentication information from a domain controller, or any of those non-SQL related things that the operating system is way better at, the SQL OS, the SQL operating system, has to transfer control to Windows' scheduler because it's calling out into the Windows API, which means SQL OS no longer has control. Now what used to happen, and this is back 2000 era, is those threads would just appear to be running and running and running and running and running. You couldn't do a damn thing about them. You couldn't kill them because they weren't under SQL OS's control. And you saw these, hang on, why is my stuff just running like crazy? What happened since 2005 is that when SQL calls out to Windows to invoke some API call, it posts that thread as having a preemptive wait. Difference here is that your thread is not suspended. Normally, when you go out, when your thread gets kicked into or when your thread relinquishes the CPU and goes into the waiting list, it normally acquires a status of suspended. Suspended if it's in the waiting list, runnable if it's in the runnable queue. If you've got a preemptive wait, the status will still be running because the query is still running. But it's accruing a preemptive OS wait type to indicate that it's not under the SQL OS's control any longer. It's running out in Windows. So technically, these aren't actually waits. If you see a thread, if you see in waiting tasks a thread under preemptive, or if you see in OS wait types high preemptive waits, what that means is that SQL spent a lot of time having Windows run stuff for it. Those threads weren't sitting waiting, they were off doing other things outside of the OS's control. What you do about these, I don't know, depends completely on the preemptive wait. There's a whole boatload of these things. I think there's over 80 of them in 2014. If you are seeing very high preemptive waits of specific types, The wait types are always of the form preemptive underscore OS underscore something else. That something else is a Windows API call name. Take the something else, go and look it up in the MSDN documentation, as in the Windows developer documentation. That'll give you an idea what SQL is busy doing outside of SQL. Write file gather, you might see. That's literally, there's, as I said, the whole pile of them. Authentication ops, domain controller. You'll see some file operations, could be zeroing out files. But yeah, take whatever is after the OS. That's your API call. That'll give you some indication of how you debug these things. But keep in mind, these are not waits in the sense that the thread is suspended waiting for a resource. The threads are running waiting for Windows to complete something. There's a slightly different meaning to these than the other waits. Happiness? Yes, sir.
So it doesn't yield.
It's not, no, it can't yield. A thread that's running in preemptive mode cannot yield because Windows doesn't know anything about SQL cooperative multitasking, so Windows will just simply run and run and run and run until it's finished.
And that will generate another wait, like non-yielding.
No. The question about non-yielding, you'll never see a non-yielding well, you could, no, you can't. You can't see a non-yielding scheduler for a preemptive. By definition, anything that's under preemptive OS something is non-yielding because it's running under Windows's control. Windows is a preemptive multitasking. SQL OS cannot control that. So essentially what this means is that SQL has given control of that scheduler to Windows and posted a preemptive wait until Windows finishes with it. It's not considered non-yielding because it can't yield. It doesn't know that it should yield. Windows doesn't have a clue about yielding processes. That's not how it works. Is there a question, Meg? Okay. So, any other questions about these? Are a little weird. You shouldn't see these things really high in general. If you are seeing really high preemptive weights, there's probably something going wrong. What it is going to completely depend on what the preemptive weight is, though. Yeah, so as I said, it's not wait, it's just an indication that we're no longer under the SQL OS control. Something else is running. Cool, happy with that? All right, our old friend CX Packet. And I noticed Neil did leave me a whiteboard, so sweet. Okay, so CX Packet is an indication that threads are running in parallel and absolutely nothing else by itself. And the reason for that comes down to how SQL runs parallel processes. So let's say that we've got a session that has just hit a parallel zone of a query plan and has paralleled into 4 threads. 4 threads. 1, 2, 3, 4, 5. Because you'll always have the 5th one. This is execution context 0. That's called the controller thread. Its job is to do absolutely nothing other than control the other 4. The controller thread is the one that goes, is everybody finished? Do you need more pages to scan? The execution context, as soon as it starts, posts a CX packet wait. The instant it starts. It will, at the end its wait. Because let's say this is the end of the parallel zone of the query. We've combined our query. This is the serial again, for example. Our other 4 queries, I'm just going to take that. Let's take this off because it's going to be confusing. So let's just say that this is the parallel zone of the query and we won't care about what happens beyond that. And let's say that this whole thing takes 20 milliseconds. Just if all these threads are running perfectly, in other words, they are processing the query from here to here on each one, this query will still incur 20 milliseconds of CX packet wait because of the controller thread. This is why CX packet is a very misleading wait type. Because as soon as you have parallelism, your controller thread declares a CX packet wait because it is waiting for the other threads to finish. It's its job. The other fun thing is if you look at system exec requests, and you've got a query running in parallel, how many rows will you see for that query in exec requests? 1. And you'll see exec context 0. You should see the controller thread. So you see your query has got a CX packet wait. Well, why is it waiting? Why is it not doing any work? It is. You're only looking at the controller thread. So that's all you see in exec requests. So that's the best case. The worst case, let's assume that this is a table scan. So a parallel table scan. If the controller thread got the balance of work correct, each one of these 4 threads will scan 1/4 of the table. Great. If it doesn't, one thread could end up doing a lot more work than the others. So let's say that it got the balance of data slightly wrong, and this thread is finished here, this thread is finished here, and this thread is finished here, and this one only finishes here. Well, now you've got 3 threads and the controller declaring assigned a CX packet wait because they are now waiting for this one to catch up. Does that make sense? Let me see if I can generate a parallel query so that we can see what's going on. I don't know if I've actually got enough data in this database to do a decent parallel query. Come on. It would be nice if the laptop would actually behave itself once in a while. What have we got here? That one. That should do the job. No, this is still running in serial, I think. There's ways to tell, but I think that was still running serially. One way to tell if a query, very quickly, if a query is running in parallel, this is the clustered index. If it's running serially, I'll start seeing my data in order of the clustered index, because that's how it's scanning. If I get it in parallel, I'm going to see values from all over the table showing up very quickly. Love this laptop. No, I give up. It's not behaving itself. So does this make sense? So you've got to be very careful about what you're seeing. Thank you. Now you show up. 8 processes. You'd think this thing actually could run things. That's probably why. Yeah. Right. So to debug CX packet, first thing, if you are seeing a lot of CX packet wait, the first thing to have a look at is what else are you seeing? So let's take another example here. let's say that instead of this query running to completion, let's say that we had a table scan, the controller thread did indeed manage to balance the data correctly, and this session ran to completion, this session ran to completion, but this one hit any wait type of choice? Lock. Let's just say lock. Waiting for a lock. So this thread is waiting for a lock, and it's waiting for that lock for, let's just say 50 milliseconds. It's not that bad for a lock. So I'm going to take these out. So previously, this one took 20 milliseconds and finished. This one took 20 milliseconds and finished. This one took 20 milliseconds and finished. But this thread's not finished. It's still sitting waiting for a lock. So we add another 50 milliseconds to the controller thread because it hasn't finished executing. We add another 50 milliseconds to this, to this, to this. And this one, lock wait until there, and then it runs to completion. So when this query is finished, what wait types have we occurred? What wait types and how much of them have we accrued? Well, we've accrued 70 milliseconds of CX packet there, because that's the controller thread. We've incurred 50 milliseconds of CX packet here, because it was waiting for the last thread to finish. We accrued another 50 milliseconds of CX packet here. We accrued 50 milliseconds of lock wait here. And we accrued 50 milliseconds of CX packet. Okay, 50, 50, 150, 220. So we accrued, in the duration of that query, 220 milliseconds of CX packet waits and 50 milliseconds of lock waits. What was the problem here? The lock. That's the problem. That's not. That's an effect. The problem was that one of the threads was sitting waiting for a lock. Yes?
Maybe a bit of slightly off-field or left-field question, but what are when the other ones, the other threads are waiting, they finish their work, what are they waiting for?
Coordination. It depends what else is happening here. Let's say that whatever's happening after this point is a parallel exchange or something, a sort, let's say. It's got to wait for all the threads to arrive. This won't always happen. It really depends what is happening after this. Let's say it's a hash table, hash match, join, hash aggregate, or a sort, where all of the threads have got to finish before it can start its work. Yeah, well, as soon as this finishes, a coordinating thread gets signaled. It'll check the others, carry on going. It gets a little damn complicated as to who actually shouts for who. This thing's asleep most of the time, just waiting for these to finish. But essentially what we've done is we've accrued a huge amount of CX packet wait, but CX packet was not the problem. So parallelism wasn't the problem here. The problem was, well, one of the threads was waiting for a lock.
So what you're saying is don't set the server to max.1?
Unless you're using SharePoint, in which case please set the server to max.1 and throw it off a roof as well. That would be putting it out of its misery. I hate SharePoint. As the dynamics also requires CX max.1, I think. They actually can't work with it higher because they've written so badly. No, please don't go setting servers to max.1. Even if they're OLTP, it just cripples the servers these days. The problem is not that we've got parallelism. The problem is that something else is causing the parallelism waits. So if you are seeing high CX packet waits, Firstly, don't go and look in exec requests, because in exec requests, you're going to see this one. Execution context 0, you're going to see it with a CX packet weight, because of course it's got a CX packet weight. It's a controller thread. If you're seeing queries which keep getting hit with CX packet weights, go look in waiting tasks, System OS waiting tasks, and look for which one of the threads in that session is not waiting on CX packet. Because there's going to be one. There will be one thread that's either still running, in which case it won't be in waiting tasks, or it'll be waiting for something else. I/O, HUX, potentially a spot on the CPU even. These things can voluntarily yield and get tossed into the runnable queue. So if you're debugging a CX packet weight, you need to start looking at what other weights you have as well as the CX packet, because that's going to give you an idea of where your problem is. Because it's probably not the CX packet weight by itself. Okay, so that's the first thing. The other thing you want to look at is parallelism appropriate in the first place? Because in really cheap queries, the parallelism is an overhead, not a benefit. Cost threshold of 5 is way too low. I set it to 1 there to force cheap stuff to parallel. I'm not even going to try doing that demo, to be honest. It needs to be set higher than 5. What's higher? I don't know. Pick a number. There's a very complicated, very involved way to go and figure out what is a good cost threshold, and it requires a huge amount of work. Pretty much go through your entire plan cache, test each one of the queries in serial and parallel, and see what the breakpoint is. It's a huge amount of work, and personally I'm quite much more fond of just picking a number out of thin air. 25, 50, 75, 40, pick a number. If you see performance degrading, pick another number. I swear, that's actually the easiest way of doing it. So, that's the first thing. Is your parallelism appropriate? Your cheap queries probably should not be going parallel, because they will incur more overhead than they will get benefit from the parallelism. So get the cost threshold higher. Check your other weights. Are you keep seeing queries which get hit with an I/O weight on one or two of the threads, while the other ones run to completion? If you do, you're going to end up seeing a lot of CX packet weight, because those other threads are waiting for the slower ones to catch up. Parallel skew is another fun one. Parallel skew is when one thread gets more work than the others. Ideally, the coordinator thread should give each thread equal amounts of work. That's great when the coordinator can anticipate the amount of work. When it gets that estimation wrong, bad things happen. The estimation often comes from statistics. So if your statistics are completely out of whack, you're doing a table scan, you'll probably find that one thread gets 20 times as much work as the others do, because the coordinator thought it was giving them equal amounts of work. With that one, run the query with the execution plan turned on and go look at the threads. That one I can show you, if I can get this thing to parallel, that is. And parallel quickly. Right, we'll let that run to completion and carry on talking. And the other thing, and this, to be honest, is what I see most common. The combination of very high CX packet weights, usually the highest on the entire server, and sitting down at number 2 or number 3 on the overall weights latch-X. This isn't page latch, this isn't page IO latch. This is latch-X, a weight for a thread-safe memory object. Latch-X covers a whole multitude of sins, so if you are seeing high latch weights, you need to go and dig into what kind of latch weights. System OS latch stats will get you that. The most common two I keep seeing when I've got that combination of high CX packet and high latch-X is access method dataset parent or access method scan range generator. Both of those are involved in parallel table scans. So what I keep seeing on client systems is parallel queries running table scans. And the CX packet weights they incur are horrible, usually because I've got data skew and I've got other weights incurring. Because as soon as you start doing a parallel table scan of a large table, you start incurring the IO weights or other fun things. So, if you're seeing that combination, you've probably got some query tuning to do. You've either got indexes which are not supporting your queries, or you've got queries which can't use indexes, or both, most likely both. In that case, it's a case of go and find the queries which are doing a huge amount of I/O in parallel and fix those table scans, because they're often not necessary. It's often poor indexing or bad queries. Let's see if this thing worked. Still running. Yay. I wanted a slow query. I didn't quite want it that slow. Everyone kind of happy with CX packet? Yes, sir.
What's the view which connects up the control threads to the individual parallel?
System OS tasks will do the job. They're all on the same SPID. Their session IDs are identical. The only thing that differs is the execution context. So the controller is execution context 0. The worker thread, the threads that are actually doing the work are other execution contexts. Go and query system OS tasks, and you'll see the whole lot.
So could you write a really clever query to try and identify what amount of CX packet is normal weight threads and what amount is
Could you write a really clever query? Probably.
should you?
I think that one's in the, if it serves your entertainment factor, go right ahead. I wouldn't bother. This is honestly how I debug CX packet. If I'm seeing CX packet and I'm not seeing high latch X, to be honest, I mostly just ignore it and go looking at the other weights on the server. If I see the two in combination, then I'm going looking for inefficient queries. I found that works fairly well when I'm dealing with client systems. This is definitely your mileage may vary, but don't get too panicky about CX packet. This thing will be sitting into the top 10 weights of your server. I can almost assure you of that, unless you put maxstop 1 on, in which case you may still see it, interestingly enough. There's some things which can override the maxstop. Right. Happy with CX packet? Okay. If that query ever finishes, hopefully I can show you what I was trying to. All right, so SOS schedule yield, SOS SQL OS. This is the one I was talking about earlier when I said it can voluntarily get off the CPU. The while 1 equals 1 do nothing thread. It'll start incurring these. This goes back to this is a cooperative multitasking system. The definition of a cooperative multitasking system is that the threads will voluntarily yield the processor. But when they voluntarily yield the processor, they have to post a wait type. That's just how the execution model works. When you get off the processor, you've got to say Y, and the Y is the wait type. If a thread has executed for 4 milliseconds and not incurred any other wait, it has exhausted its quantum. It will voluntarily yield to the CPU. It does not go into the waiting list because it's not waiting for anything. When you've got a scheduler yield, the thread will go from the processor to the bottom of the runnable queue. It doesn't go through the waiter list at all. It's not waiting for anything. If the runnable queue is empty, it goes straight back on the processor, and it's almost instant. If the runnable queue is not empty, it's set to the bottom and bubbles slowly to the top, and then goes back on. This is where the concept of non-yielding schedulers comes in. If something has been executing for more than 4 milliseconds and has not voluntarily yielded the CPU and is not running in preemptive mode, then it is a non-yielding scheduler because it refuses to give up. And yes, it's a bug in SQL. The dev team have been very, very careful to go through any piece of code that could sit on the CPU for long periods, and put checks into it. Should I yield or not? And if so, sleep. So to be honest, those non-yielding schedulers are fairly rare. I haven't seen one in years. I used to see them on 2000 all the time. I can't remember when I last saw a non-yielding scheduler in SQL Server. It's a lot better behaved now than it used to be. All right, this is not indicative of a problem. This is not indicative of CPU pressure. The only thing that a schedule yield tells you is that you've got something that's running that doesn't need resources, or doesn't need resources that require waits. While 1 equals 1 do nothing is definitely going to start incurring these things, but it's going, unless there's something else waiting for the processor, it's going to be off, back on, off, back on, off. The other thing that tends to incur these things is index scans of in-memory indexes. And I don't mean hackathon here. I mean indexes where the memory pages are all, the data pages are all in memory. Possibly because they're hot, possibly because they just got needed. Read the page, read the page, read the page, read the page, read the page. We don't need any resources. We're not waiting for I/O latches. We're not waiting for memory grants. We're just reading along the index. Oh, 4 milliseconds is up, off the CPU. Schedule yield. Interesting thing here, you will not, if you start doing the maths to do resource wait time equals wait time minus signal, these things, of course, will have very low resource wait time. It'll be not zero, but that's because of measurement errors. When you've got wait times of 1 or 2 milliseconds, the signal wait time and the resource and the wait time itself won't be equal. It's measurement accuracy, it's nothing more. This stuff does not incur actual wait times. All of its weight is in the signal, because it's in the runnable queue. And yeah, that's all that's SOS schedule yield is. As I said, it is not indicative of high CPU. It's not indicative of a CPU problem. If you have a CPU problem, you might have scheduler yield. That doesn't mean it's a cause. And you can have high CPU without having any scheduler yield at all. Happiness? Okay. Right. Page latch and page I/O latch. Unfortunately, very easily mistaken for each other. Page I/O latch is a wait for a page to be read in from disk into the buffer pool. The type that you get on the end of this, page latch SH, page latch EX, that is determined by what operation wants the page. It's got nothing to do with how the page is getting read in. If that was a select query that was running, it took a shared latch on the page isn't there, read the page in from disk, you get a page I/O latch SH. If it's an update, insert, delete that needs the page, you get a page I/O latch X. Absolutely nothing to do with how the page is getting read in. It's completely got to do with what the page is needed for after it has been read in. This doesn't mean you have a slow I/O subsystem. One very common thing I see lately is bad indexing, bad queries. We're reading a huge amount of data that we don't need to be reading, which means we're requesting a lot of data from the I/O subsystem. The I/O subsystem is quite capable of handling the load, but if we're reading 10,000 pages in half an hour and incurring 10 milliseconds of page I/O latch wait on each one, 10 milliseconds, by the way, is really fast for an I/O subsystem unless it's SSD, even if it's SSD, to be honest. You're going to be incurring quite a lot of page I/O latch just because of the volume of pages you're reading in. So to be honest, if you're seeing this, the first thing I'd ask is, do you have buffer pool churn? Are you using that buffer pool efficiently? Are your queries constantly displacing data from the buffer pool just to read more in? Read data in, throw it out, read more data in. You're going to start seeing that when you look at your page life expectancy. Look at it on the node level, not for the entire buffer pool. But if you're seeing really low page life expectancy and high page I/O latch weights, you've got a case of buffer pool churn. You're just churning data through the buffer pool. Could be you need more memory. Could be you've got inefficient queries. queries which are doing table scans instead of reading 3 pages. But most of the time, your page I/O latch weights are this, not an I/O subsystem problem. It could be an I/O subsystem problem, but you probably want to discount all of that before you start looking at the I/O subsystem itself. But go look at perf counters, go look at the the disk latency figures. If the disk latency figures are sitting in 400-500 milliseconds, yeah, you've got a slow I/O subsystem. I've seen an I/O subsystem a few years ago that had a 1.2 second latency on it. Yeah, I know. I mentioned that one to Bob Ward, and his comment was SQL can't handle that. It's handling it just fine, actually. Barely. But yeah, we did have it. Sustained, steady at about 1.2 seconds. Thank you, disk mirroring. That was write latency. Read latency, SQL's not quite so happy about. Write latency, it actually can handle. Not well, but it can handle it. But yeah, so go look at your queries, go look at your indexing long before you go and look at your I/O subsystem and complain that it's inefficient. It's probably a case that's just been put under way too much load. Okay. The often mistaken for the former, page latch. A page latch weight is a weight to modify a page in memory. It's got nothing to do with the disk at all. When a row is added to a page, SQL's got to make some changes to the page header. The page header contains information such as how many rows are on the page, how much free space is on the page, where the rows are on the page. You can't have 2 sessions writing the header at the same time. The mess would be abysmal. So anything that wants to write the page header, footer, put a row on the page, has to take a page latch in exclusive mode so that it can go and do that. Anything that's reading a page takes a page shared latch to ensure that the rows aren't going to appear or disappear while it's busy reading the page. By the way, this is why in-memory, and by this I do mean Hackathon, is so much faster, because it doesn't have the page structure, it doesn't incur page latches. Page latch weights, most common 2 I see, are page latch UP, page latch update, in TempDB. By the way, as far as I'm aware, the only time you'll see a page latch UP is on an allocation page. Normal data and index pages don't get latched for UP, they get latched for shared or exclusive. Your allocation pages get latched for UP, update. That's your GAM pages, your SGAMs, your PFS, your IAMs, and all the other allocation pages scattered through a SQL database. If you're seeing page latch UP in database 2, you've got allocation contention in TempDB. Please go create some more data files. Same size, can be on the same disk. Because this is not an I/O related latch weight, this is an allocation, this is a contention on the page. So if you're seeing UP, TempDB, you need more TempDB files, and or you need trace flag 1118. I'll leave that, that's homework for the reader, go read. Now, Paul Randall's got a whole bunch of blog posts on that trace flag. What it does is it reduces the need to update the allocation pages in TempDB when you're creating new temp tables. So it alleviates TempDB allocation contention. This is the most common place I see page latch weights. Page latch weights in user databases tend to be pretty rare. You will see them occasionally. By the way, I have heard of a case recently of page latch UP in a user database, which meant they were allocating new tables or new indexes in a user database fast enough to overwhelm the allocation, fast enough to cause allocation contention. The comment to that was, what the hell are you doing with that database? And they were actually using it as TempDB, creating and destroying permanent tables with randomized names to avoid using TempDB. Please don't do that. TempDB is optimized for random table creation and drops. User databases are not. You can hit allocation contention in a user database quicker than you can hit it in TempDB, because TempDB is designed to not get this any longer, especially in 2016, by the way. User databases, I've only seen one case of this recently, and that was PageLatch X in a user database. And these guys were inserting into an ever-increasing index. Now, clustered indexes on ever-increasing keys are a good thing because they don't give us page splits. But it does mean you're inserting into one page. Anything that wants to insert into a page has to take an exclusive page latch on that page so it can put the row on. Have multiple things trying to insert into a single page? Yep, guess what? You get insert hotspots. They're pretty rare. You've got to insert at one hell of a speed to get those things. These guys were. They actually managed to get page latch X weights on a normal table in a user database because they were inserting into one page so fast. Yeah. There's two potential causes of page latch X and SH weights in user databases, and they're completely the opposite advice on them. So either you're getting excessive page splits, and because you insert it to a page, the page has to split. Page above it might have to split. All those page splits means a lot of work goes in to put the index structure back as it should be. Every single one of those pages needs exclusive latch taken on it. If you're seeing that, you probably want to change the index so that it's not splitting so often. Alternately, you could be getting an insert hotspot on an index, which means that you're not getting page splits because you're inserting everything into one page. You might want to change your index so that you're inserting into multiple places in the index. Good luck working out which one you've got. Actually, you should know, you can tell which you've got by looking at the insert patterns, looking at the fragmentation, looking at the index's design. The insert hotspot was inserts of an identity into an identity column that was a clustered index. And as I said, you do need a fair rate of inserts to get that kind of behavior. All right, page latch. I think I've only got, okay, two more to go. So I/O completion. Anyone got I/O completion as one of their top weights that they know of? You shouldn't. This one's shouldn't be that common. I have, however, seen a whole bunch of blog posts that say I/O completion is a high weight. You should go and optimize your queries. No, because it's got nothing to do with that. I/O completion is not reading data pages into cache. It's not got anything to do with data pages and the buffer pool. I/O completion occurs a bunch of places. When you're reading the transaction log, rollback's not the only place you'll see this, but it is one of the more common ones. I think you get this as well when you're restoring a database and doing crash recovery, or bringing a database online and doing crash recovery. Anything that requires reading the transaction log. I don't know which allocation page reads get this one, so I'm going to ignore that. Allocation pages, for the most part, are in memory anyway, because they're used frequently. It's not very common to be fetching allocation pages from the disk. The other place you'll see I/O completion is when your sorts spill to TempDB. If you've got sorts that are not requesting enough memory to sort in memory, they spill to TempDB and they incur I/O completion weight. If you remember earlier on, hash tables which spill to TempDB incur sleep task. Hash sorts incur I/O completion. Don't we love consistency? Don't know. I suspect there's some legacy reasoning there. Maybe it'll change in a couple of versions. And if you're seeing async I/O completion as opposed to I/O completion, it's probably related to backups. It's the majority of the time that you see async I/O completion is when you've got backup operations, or if you've got doing very heavy checkpoints, you'll see it there as well. Happy with that? You understand the difference between this and the page I/O latch weights? So they do measure very, very different things. And the last and my favorite is async network I/O that has nothing whatsoever to do with the network. Usually. It is possible for this to be caused by the network, but if it is, you're probably using a WAN or something slower, because this is not going to be caused by a normal LAN. Async network I/O is a wait that measures the time that the client application takes to accept the data and acknowledge that acceptance to SQL Server. So it is the entire round trip from SQL sending the data and the client application saying, got it, thank you. Which is why it's called async network I/O, because network. However, I can trivially and without any work whatsoever generate a crapload of async network I/O wait on this laptop with a local instance of SQL Server by running Management Studio. Because Management Studio incurs async network I/O waits, Management Studio causes async network I/O waits at a huge rate because it's really, really inefficient at displaying data. You kind of have thought it would be decent at that. It's kind of its job. The majority of the time you see async network I/O waits in a production server, either lots of people are using Management Studio, yay, or the client application is processing the data inefficiently. Get one row, display it on screen, log some stuff, tell the user, get the next row. Oh, got 50 rows, thanks SQL Server. That will incur huge amounts of async network I/O. Client applications should accept the data, put it in a buffer, and then process it. Most of them don't. Most of them will take one row at a time from SQL Server and do stuff with it. Row by row processing on the client, and will cause huge amounts of this. It's not uncommon to see this as one of the top 5 weights on most systems, just because of the way the client application has been written. Happiness? Okay. And that is pretty much my list of weights that I see badly misinterpreted. Paul's weight library. Every single weight in SQL Server is in that. A lot of them don't have descriptions yet, but if you bug Paul, I'm sure he'll be happy to add them. What he's done is added the call stacks for common causes of it. So, for example, I/O completion. At the bottom of the page it says it can be caused by this, 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 and this, and posts example call stacks of all of them. So if you've got a particularly problematic weight, get your call stacks from extended events, go over to Paul's library and see if you can figure out a match. If you can't, he says you can mail him with the call stacks. He'll be happy to look at them. Knowing Paul Randall, you'd probably make his day if you sent him a complicated call stack that you couldn't understand. He tends to enjoy that kind of thing. And then this is his blog post about getting the call stacks via extended events. It has a link to his other blog post about getting the public symbols down. And that is roughly more or less me done on weights. And I think I even have a minute to spare. Let's see if that query ever finished. Thanks, Management Studio. Yeah. Did we mention Management Studio is a pile of crap? If you do want to see any examples of that, come back to me later. I'm sure I can find a query that does behave itself and doesn't run out of memory too quickly. Other than that, I think I've got about a minute or two left, so I'll...
By the way, Paul's weight stats library.
Yes.
He's actually asking for people to help fill that in.
Ooh.
I've volunteered, so I'm...
Okay, so apparently Paul's asked for people to help him with that weight stats library. So, anyone got some really, really weird weights to send him?
I've sent him the mail. He sent me a mail back. He says he's a list, and he'll give you like how to generate the different ones, and then he wants you to fill in the call stacks for them.
Yeah, but so that library is fleshing. It's getting fleshed out. It's not complete yet. It is getting there. It's still a phenomenally good resource. So, I think I've got a minute or two left. Any questions, quickly? No. I've worn everybody out. Okay, in that case, thank you very much.